In this video, we'll continue our discussion of polar integration with another example. So we're finding the volume between a surface z equals 16 minus 4 times x squared plus y squared. And hopefully you can see what that is, potentially. It is a paraboloid shifted up 16, turned over, upside down, opening down, and then stretched by a factor of 4. So it's going to be a lot skinnier. And it's also moved straight up, so it's right above the region that they're going to give us. They want to know the volume between that paraboloid and the xy plane, which is flat there, right? Z equals 0. So I'm going to write that down because we're eventually going to be heading towards that, and it's a good thing to note that, okay, the xy plane is 0, and then the surface here, and remember that we want the area or the volume between we take top minus bottom. So what we're looking for is a region over the region R that we have here. This is region R of this surface, and it's this minus that. Okay, well, that's just the one on the right. And then dA. I'm just writing that down so we can see where that comes from. That's just the top Z minus bottom Z. Now, they gave us that it's bound by the cylinder. So we're looking at that paraboloid, and then we're looking at a tall cylinder, right? Like some kind of can, something like that, shooting straight up infinitely. There's my region R with the radius 1 in each direction. This is going to help me out discover or pick what my R is and what my theta is. And we can tell we want to go to polar because it's circular. Well, R, we just start in the region, or at 0, 0. And if it's in the region, we count that as 0. And then going out, we go out, it is constant, it's going to be a constant 1. So R is between 0 and 1. We get the full circle as well, so theta is going to be 0 to 2 pi. All right, so let's rewrite our formula. We always put theta on the outside. And then R equals 0 to R equals 1. Then I have 16 minus 4 times, okay, x squared plus y squared, remember, is r squared. That's why this calls for polar. Times, okay, I'm going to put all that, and then remember, when we switch here, we got to add an r dr, d theta. All right, so this integral is equal to, okay, I keep everything the same. I'm going to simplify the inside. Just distributed the r. And thankfully, this is just straight integration there, power rules. So we got theta from 0 to 2 pi. And then we're going to integrate this stuff. Okay, I up the power and then divide by the new one. So it's 8r squared. And then minus r to the 4th. And this is ran from r equals 0 to r equals 1 d theta. I like these because, as you can tell, it's just going to be a constant. Very nifty there. All right, so 0 to 2 pi. I don't know if I've ever said nifty in my life. This is going to be plugging in R1. I got 8 minus 1. Plugging in 0 is just going to give me another 0, d theta. So I know that I'm going to have theta equals 0 to theta equals 2 pi. 8 minus 1 is 7. Cool. Nice, easy integral. I got 7 theta. Ran from theta equals 0 to theta equals 2 pi. The 0 is just going to make a 0, so all I'm doing is plugging in 2 pi. That's going to give me 14 pi. So the volume of that paraboloid down, caught by a cylinder, is 14 pi. Polar makes things nice and easy when it calls for it. If you try to switch something that's very rectangular to polar, it's going to be very difficult, hence the reason that the circular stuff is very nice with polar. We're going to extend this a little later into 3 dimensions with 2 different systems, and we'll get to that point.